Alright guys, this is your Unit 2B video. I have highlighted some problems I'm going to go through. And that's about it. Just going to scroll back to the top. So starting with question 4. What is a possible equation of the graph to the right? Okay, so first thing you need to figure out when you look at this is where the intercepts are occurring. And by intercepts, I mean x-intercepts. So if I zoom in here, this is your origin. This looks like -3 and 0. And I think, all right, the factor that would give me a root of -3 is x plus 3. The factor that would give me a root of 0 is x. Since there is a kiss in the x-axis, meaning it touches it once, that means it must be an even multiplicity, so I'll add an exponent of 2. So right now I'm thinking f of x equals x times x plus 3 squared. Now one other thing you need to pay attention to is the end behavior. This would be a degree 3 polynomial with opposite end behavior. Since it's ending negatively, that tells me there must be a leading coefficient that's negative. And now I'll look at my options. Okay, so leading coefficient needs to be negative, so I can eliminate options A and B. And the one with the correct exponent on the x plus 3 is option D. So still referring to the graph to the right, the only interval that the function is increasing on from left to right is right there. Now remember, we only care about our x values when we're stating our intervals. So from -3 to -1, we are increasing from left to right. So that's option C. Now referring to the function on the right, I want to know on what intervals it is negative. So that means below the x-axis. So I'm seeing, I'll zoom in here, a couple intervals. Here, maybe I'll just highlight. Here, and here. That's where the function's negative, because it's below the x-axis. Okay, so if this is the origin, this looks like -3, -2. So my first interval is from -3 to -2. And then this looks like 0 and 2. So 0 to 2. So the interval where it's negative is -3 to 2, -2, 0 to 2. Where it's not negative, it's positive. So I didn't ask for it, but technically I'm positive from -infinity to -3, -2 to 0, and 2 to infinity. In order to algebraically determine if a function is even, odd, or neither, you're going to evaluate the function at -x. So if you evaluate a function at -x and you get the original function back, that means it's even. If you evaluate it at -x and you get the function back, but it looks like it's been multiplied by -1, then it's odd. If neither of those situations happen, then it's neither. So for example, I'll plug in -x from my first function. And this is where you really need to not be lazy with your parentheses. And I'm seeing a -x raised to the 4th power. Any negative number raised to an even exponent will end up being positive. Now here's where some students get stuck. Order of operations here. I'm doing -x squaring it. That would be a positive x squared. But then we're multiplying it by a -1, which would create a negative x squared. And then plus 7. Now what you're going to do is compare this to the original function. Did I get the same thing back? Yes, I did. So that means I just showed that evaluating the function at -x gave me the original function back, meaning I got the same thing. So therefore this function is even. Now C is where things get a little bit weirder. If I evaluate the function at -x, actually this one's not too weird. I'll talk about weird in a second. Okay, a -x squared is a positive x squared. Same thing down here. -x squared is positive x squared. Okay, I got the exact same thing back, which means that it would be even. Let's pretend I change this exponent to be 3. So let me just change the problem real quick. if this was an x to the third in the numerator, then the numerator would become negative x to the third over positive x squared minus 4. Since this is the original function x cubed divided by x squared minus 4, where it looks like just the numerator was multiplied by negative 1, that would then be an example of an odd function. Okay, so again, I changed the problem here to make it more interesting. If this was an x cubed in the numerator and I evaluated the function at negative x, this looks like the original function c of x, which was this, then multiplied by negative 1. Okay, so in that case, that would be odd. Keep in mind the original function, though, when it was an x squared, actually was even because you got the same thing back. But I had just changed that to make it an interesting talking point. Now, as far as how they graphically look, a function is even if it's symmetric with the y-axis. It's odd if it's symmetric with the origin, which means if you rotate it about the origin, oopsies, 180 degrees, it looks exactly the same. And then neither means it has neither of those symmetries. So for example, the first one here is symmetric with the y-axis, so therefore it's even. This one over here, if I were to rotate my tablet 180 degrees, this function would look exactly the same, so therefore it's odd. But this one is neither symmetric with the y-axis, nor if I rotated my paper 180 degrees, would it look exactly the same. So that's why this one's neither. So that's even, odd, and either. Okay. If I give you a function and I want to know its zeros, in this case, it's already factored for me, so I just have to set it equal to 0. So I'm noticing that I would get x equals negative 1 as one of my zeros, but it's occurring 3 times. So that's a multiplicity of 3. This is x equals 1, but it's only occurring once. And x squared minus 4, you could factor that or add the 4 over and take the square root. You would get 2 solutions here, plus or minus 2, each occurring with a multiplicity of 1. As far as the degree goes, you could either imagine what the highest power would be if you multiplied it all out. So like this would be an x to the third, times another x would be an x to the fourth, times an x squared would be an x to the sixth, or count up your multiplicities. So like this one's occurring 3 times, plus another one would give me 4, and then 5, 6 for each of these roots separately. So this would be a degree 6 polynomial. Now, since the leading coefficient is positive and my degree is an even number, that tells me that my end behavior is the same and it must be going up. Okay? So that's where you guys just really have to have your end behavior memorized. So if I actually scroll up to my cover sheet here, this is the end behavior you need to know. If the function is an even degree, it'll either both be up or both be down, depending upon if the leading coefficient is positive or negative. With an odd degree polynomial, I remember that if the leading coefficient is positive, it ends positively. If it's negative, it ends negatively. But what you need to know is an odd degree polynomial has opposite end behavior, as where even has the same in either direction. So make sure you guys know this. That's why I put it on the cover sheet. Okay. I think I stated everything I needed to state here. I found the zeros, I stated the degree, and I sketched the end behavior. Now, if it asked me to describe the end behavior, which it didn't here, if I describe, it would be as x approaches negative infinity. So that's as you look to the left. That's my left arrow. My function would be going up. So I'd write f of x approaches infinity. It's a terrible infinity. In the other direction, as x approaches infinity, so that would be as I'm looking to the right, I'm also going up. So f of x approaches infinity. Okay, I'm going to delete this so I have some space. For question 4, I'm going to algebraically determine the zeros of this. First thing I'm noticing is I have a negative leading coefficient, so I'm going to factor that out. Okay, since there's 4 terms, this is likely a factor by grouping. Oops, minus 4. Okay, and I'm recognizing that I actually could factor this further. And that's negative x plus 2, x minus 2, 3x plus 1. And that's completely factored. So by completely factoring this and setting it equal to 0, I see 3 zeros. Negative 2, 2, and negative 1/3, because I would subtract the 1 and divide by 3. Each with a multiplicity of 1. Now, if I want to find the y-intercept, you're going to plug 0 in for x. So if I come back to this function and put 0 in, this would be negative 3 times 0, which is 0, minus another 0, plus another 0, because anything times 0 is 0, plus 4. So it's pretty easy to see that my y-intercept would be 4. I'll come back to the mins and maxes because I got to do that in my calculator, which looks like I actually have to do it now. So 1 second. Okay, I've plugged it in. I'm going to use a standard window. And you'll see that I'm actually missing a maximum at the top. So I'm just going to adjust my window so that I have a y max, or excuse me, this should have been 10, where I have a y max of like 20. Let's see if that captures it. And there you go. So just like how I show in another video, if I want to capture, say, the maximum, I would do second trace, option 4, which is our maximum. I just got to be to the right of it, be to the left of it, get those arrows to pinch in so that we capture the maximum, and hit enter again. So the maximum is approximately 1.049, 12.0246. Okay? Yeah, 1 second. Trying to keep my videos short, so I just paused it so that I could sketch this out. You'll see that I actually included the zeros because I found those algebraically. Negative 2, negative 1/3, and 2. All right, I'm going to go ahead and find this minimum now. Okay, so I'm just going to write that down. Okay, and so I've labeled this. So now I actually have everything I need to go ahead and answer my questions. And just so you guys are aware, when I ask for max value and min value, technically it's really just the y values there for C. Okay, so I'm actually going to skip D. I'm going to go to E, where the function is increasing. From left to right, we are increasing right on that interval. Now, I only care about the x's. So I'm increasing from this x to that x. So my interval of increase is negative 1.271, 1.049. Okay? I am decreasing from negative infinity to that x value, and from this x value to positive infinity. So again, I only care about my x's, negative infinity, which would be out here, up until this x value, then 1.049 forever, so towards infinity. All right, let's say I want to write a polynomial function with the following zeros and multiplicities. Which again, multiplicities just mean how many times the root occurs. Going down the line, I'm just going to write a factor that would give me each of these roots. So like a factor of a root of 5 would be x minus 5, x minus 2, x plus 3, x plus 1. Okay, so each of these factors would give me roots of 5, 2, negative 3, negative 1. Just thinking backwards. When it tells you multiplicities, that's just how many times it occurs. So this is technically occurring once, 4 times, 5 times, once. So if you want to know the degree of a polynomial, you would just count up its multiplicities in its factored form. So 4, 5, 6, so this is what, 9, 10, 11? This would be a degree 11. Now, it doesn't ask for it, but I could tell you the end behavior of my possible function because I made the leading coefficient positive. Since it's degree 11, that's an odd degree. Since I made the leading coefficient positive, it'll end positively. So if I were to plug this in, I would expect that to occur in my calculator. All right, I'm next going to curve sketch this function where I'm going to algebraically find its zeros by factoring. Okay, so I'm looking for factors of 36 that add to negative 13. So that would be 9 and 4, so negative 9, negative 4. Okay, now when you factor this, it's not going to be x times x because that would give you an x squared. You want x to the fourth. So we'll do x squared times x squared. Minus 9 minus 4. Because then my inner and outer terms would sum to a negative 13x squared. If I want to find my zeros, I would set each part of this equal to 0. So keep in mind that this would be x squared equals 9. So x equals plus or minus 3. Okay, so what I'm seeing are 4 separate roots, and they're all occurring once. And that's corresponding to my degree 4. Since the leading coefficient is negative, that means that we are going to have end behavior that looks like this. Okay, again, because the degree is even, it has to be the same end behavior in either direction. Since the leading coefficient is negative, it's got to be down. Okay, what else do I need? I need the y-intercept. Y-intercept occurs when x equals 0. So if I go up here, this would be 0 plus another 0 minus 36. So that tells me my y-intercept is negative 36. Okay, and I should have enough information now to graph my function. Okay, so I am going to touch the x-axis at negative 3. I should zoom in here. This is hard. Negative 3, negative 2, 2, and 3. Now, since each of these roots only occurred once, that means I will cross the x-axis. Additionally, remember I need to cross the y-axis at negative 36, so maybe I'll go by 6s. This would be negative 36, because I'm doing by 6s. And my end behavior was down in both directions. Okay, so I'll fill in my end behavior. Everything to the left of negative 3 must be down. Everything to the right of 3 must be down. I must cross, and then cross again. I've got to hit the y-axis, go up to 2, cross, go back to 3, cross. And that completes my function. Okay, and the reason again that I knew that I had to cross at each of these intercepts is because each of these roots had a multiplicity of 1, which is an odd number, and odd number multiplicities correspond to crosses. Okay, had any of these roots occurred again, that meaning it occurred twice an even amount of times, then it would correspond to a kiss in the x-axis. Okay, the last problem I'm going to talk about in our packet here is number 8. A rectangle is bounded by the x-axis, and the curve y equals negative x squared plus 10 is shown in the graph below. So here's my parabola. I have a rectangle that's contained under it. I want to express the area of the rectangle as a function of x and a value of x to the nearest hundredth so that the area is maximized. Okay, what you guys need to recognize is that the area of any rectangle is length times width. In this case, our length is symmetric about the y-axis in either direction, so some x distance to the right and some x distance to the left. So that's twice however many x's in either direction. Okay. This would be a y value because we're following the y-axis. So, for example, right now the rectangle that we have is 2 to the right, 2 to the left, so technically a length of 4. And the height is approximately what? Like maybe 5? 10, 9, 8, 7, 6. Okay, 6. So technically this is 6. That's just one example. But I want to represent any possible rectangle I could create. So like I could drag this point, and this would create another rectangle that looks like that. Okay? I want to figure out what the maximum area rectangle is that I could create so that it's under this parabola, but also bounded with the x-axis. Okay? Now, keep in mind that this y function is negative x squared plus 10, I think it said. Yes, plus 10. Okay? So, in order to talk about the area is length times width. It's going to be 2x times y. We just said that any y here is going to be represented by negative x squared plus 10. Okay, think about that for a second. Let's say x was 2, just like what you guys were seeing here. Then the y value would be negative 2 squared plus 10, which is 6. Okay, so that would correspond to a length of this. If x was 1, so a little bit more than that, less than this, I should say, your rectangle would kind of look like that. So then your corresponding y value would be 9. So this function, this negative x squared plus 10, is just representing any possible height that you could have. Okay, so that means that this function that I've come up with, 2x times negative x squared plus 10, will represent the possible areas of the rectangles that can be created under this parabola with those constraints. So this is what I'm going to plug in my calculator. Okay, so if I do a zoom 6, that'll reset my window from any previous problem. Okay, and you got to see I got to adjust my window here to find this maximum value. So I will do second table to see where my function's at. Okay, and at x equals 1, it's at 18. At x equals 2, it's up to 24. So maybe I'll change my y maxes to like 30. I always overestimate. And there you go. That's the maximum I'm looking for, because I'm looking to maximize the area of this rectangle. I don't care about any of the negative x's over here because I can't have a negative length in the context of this problem. So I'll do a second trace, find my max, which is option 4. To the left of it, I'll hit 0. To the right of it, maybe I'll hit 10. That should capture it. And there you go. So let me sketch a picture of this. Okay, so all I've done is I've sketched a picture to the left of what this graph looks like. Here's the maximum with its labeled of the coordinate point. So it says to the nearest hundredth, what is the maximum area? The maximum area is the 24.34 number, because that is representing the y values. A is the y value. Like when you put this in your calculator, you're telling the calculator y is my area. So keep in mind what this means is that if you want to create the biggest rectangle you can under this parabola bounded with the x-axis, you would have to go out, let me erase all this for a second, you would have to go out about 1.83. So like we'll say 1.83 is maybe like here. 1.83 on your x's. And then 1.83 in the other direction. And this rectangle that's created, that would be the biggest rectangle with the largest area that you could create. And the area of that rectangle would be 24.34. Okay, so that is the conclusion of this video. I will likely combine this video with the other video I made, which was on the modeling problems, just so that it's all combined in one video. So that's about it. In this video, I'm going to go through some modeling problems from the modeling review sheet, specifically questions 3, 5, and 6, just to get a good variety. Alright, so coming to 3. Square of side length x are cut from the corners of a 30 by 45 inch piece of cardboard. 30 by 35. So we'll say that this is my 30, this is 35. And an open top box is created by folding up the flaps. Find the value of x that will maximize the volume. Round to the nearest hundredth. Okay, so in this rectangle, we're cutting out squares from each of the corners. And I don't know the dimensions. We'll call them x by x. Once you cut them out, you're going to fold along the dotted edge. Okay, which will then create a new box that looks like this. Okay, where the length and width of the base are corresponding to this. And the height, the part you fold up along, is corresponding to the x. Okay, so you had 35 across here, but you've taken away 2 corners of x, so this length is now going to be 35 minus 2x. By that same logic, on the other side, you had 30, you're taking away 2x, it's going to be 30 minus 2x. So, if we're talking about the volume of the box, volume of any prism is area of the base times the height. So I'll do x times 30 minus 2x times 35 minus 2x. And this would be a function that would model the volume for any value x that you would cut out of the corners of this box. Now is where you go to your calculator. Okay, so in my calculator, I've plugged in the function. If I hit a zoom 6, which is my standard window, you'll see that it's not exciting at all. Nothing's happening. So that means my graph is just not in this visual window. So what I'm going to do is go to my table of values to see where the graph is at. And you can see that at x equals 1, I'm already at like 900 something. Go up to like 2,500 and then we start to come down. So I'm going to guess here that I'll change my y max to, wait, what did I say? Maybe like 3,000. Hit graph. There you go. That's the maximum we're talking about. Remember, we don't care about anything on the left because that would mean x is negative. And in the context of this problem, you can't have a negative x because it's representing a distance. Okay, so this is my graph. I'm just sketching a picture of what it looks like. Okay, this maximum I'm going to find using my calculator by using second trace. I'm looking for a max, so that's option 4. Left bound, I'll get to the left of it. So I'm going to say 0. My right bound, and guys, you can just type in a bound too. Like, I can type in 10. I know over here is 10. You'll get the arrows to pinch in on that max, and you'll see it there. But just to show you again, second trace, max, you just have to move the cursor to the left of the maximum. Hit enter. Get to the right. As soon as this wants to go. Come on. The arrows pinch in, hit enter again. There you go. So to the nearest 10th, I think I said? No, 100th. To the nearest 100th, that's 5.37. 509.12. No, 2509. Oopsies. Okay, so the question is asking for the value of x. This is your value of x. And it's asking for the maximum possible volume. That's your volume. So what this means is if you want, based on the dimensions of this rectangular sheet, to create the biggest possible box, you would have to cut out squares from each corner that were 5.37. And the maximum volume that would come about is this 2,509 number. A cookie company packages its cookies in a rectangular prism box designed with a square base that has both a length and width 4 or less than the height of the box. Okay, so I'm going to draw a picture here. I'll actually have it on its side. So it's got a square base, and it says that the length and width are each 4 inches less than the height of the box. So actually, let's call the height x, and then each of these would be x minus 4. Right? Because the height would be going deep into the page here, we'll call that x, and then the length and width, which would be of the square base, because it has to be the same, would be 4 less than x. Okay, so now a polynomial that represents the volume, again volume is length times width times height, so x times x minus 4 squared we'll say. Okay. Oh, and I even said write a polynomial function that represents it with the height x, which is what I've defined this as. Find the dimensions of the box if the volume is 128. Okay, so I'm plugging 128 in for v. Alright, so it wants me to algebraically solve this. So let's see. So I can see 128 equals x times x squared minus 8x plus 16. That's by me foiling that out. Okay, and then I'd set that equal to 0 by subtracting the 128. Okay. I'm going to see if this factor by groups. I can pull out an x squared. And maybe I can pull out a 16. What is 128 divided by 16? I quit out of this. Good, so I can pull out a 16. So now this gives me x squared okay, this would not yield a real solution, but I can get x equals 8. So what that tells me is this is 8, and this is 4, and this is 4. Now this should make sense because if I go in my calculator, when I do 8 times 4 times 4, I should get 128. And I do. Okay, last problem I'm going to do is with the cylinder. The volume of a cylinder, which, remember, a cylinder looks like this, with a top and bottom, is to be 400 cubic centimeters. So they're giving you volume. I want to determine the radius and height of a cylinder that uses the least amount of material. Whenever we're talking about material, that's surface area. Now the surface area of a cylinder is 2 pi r squared plus 2 pi r h, where the 2 pi r squared is referring to the two circles that make up the top and bottom, because the area of a circle is pi r squared. So let's do 2 circles. And then the 2 pi r h, if you recall from geometry, is your lateral area. So that's the stuff that goes around the cylinder. Okay, so volume of any cylinder, because that's what they gave me, is 400 here, is pi r squared h, because it's the area of the base, which is a circle, pi r squared, times the height of our cylinder. Okay, now at this point, I need to use this info about the volume and plug it into the surface area formula. So what I'm noticing is I have an h and an h. So I can rearrange the volume info by dividing by pi r squared and taking this and subbing it in for h. Okay? Just so that you guys know, when I plug this in my calculator, this portion, I'm going to have to make sure I'm very careful. I'm going to have to use a bunch of parentheses to make sure I'm telling the calculator 400 divided by the product of pi r squared h, because the calculator I have on my computer is an older software. But if you have one of the newer ones where you can actually insert a fraction in your y equals, I would recommend doing that. So we're going to plug this into y equals, and keep in mind that I don't have an r that I'll use, so every r will just be an x in this case. So be aware. So x will equal our radius. Y is equaling our surface area. Okay, so here we go. Okay, so like I said, my y equals is going to look kind of weird because this is older software. So if you have an older software calculator, this is how you want to plug it in, where I had to do with the 2 pi r, in this case x, 400 divided by, and then I needed extra parentheses around the pi x squared or pi r squared. Okay, so I'll hit graph. This is actually the same window I used for another problem, so it might actually work for me. Look at that, it does. Okay, I don't care about all this because this would represent a negative x, which would be a negative radius. I can't have that. I just care about this quadrant 1. This function is representing the surface area. So as you can see, we use a lot of material, then we start to minimize the material, and then we start to make a lot of material again, or use a lot of material again. I want this min value. So I do second trace, min. And there we go. I'm rounding to the nearest whole number, it says. What does it want? Determine the radius and height of the cylinder that uses the least amount of material. So the radius to the nearest whole number was 4. The surface area is about 301. Okay, so again, this is my radius, this is my surface area. If it wants the height was based off the radius. The height, we have a formula up here, is equal to 400 divided by pi r squared. So I'm just going to plug 4 in, and then we'll round that to the nearest whole. So about 8. Okay, so again, going back to the problem, what that means is our height is approximately 8 centimeters. Our radius is approximately 4 centimeters. So something that you could do is do a little check here. Does that make sense? If you plug 4 and 8 in for your volume formula, do you get about 400? Keep in mind that you rounded. So this would be pi r squared h. And I do get a little bit more than 400, but keep in mind we did round these, so that's a pretty good check.